Hello. I thought we'd do some problems from chapter 1. Going to work on some fundamental problems just to show you the basics of how to do some of these problems. So we're going to start. We're going to look at this problem right here. Fundamental problem 1-15. We have some plates, 2 plates on this side, 1 plate on that side. They're held together by 2 3/4 inch diameter bolts. And we're going to find the maximum average shear stress developed in each bolt. Okay, very straightforward. Note that these 2 fasteners are in double shear. You have 2 plates, right, on this side and 1 on that side. So they're in double shear. So this is basically the free body diagram of the entire structure. We don't have to duplicate that. But let's do a free body diagram of the fastener. So as I said, we've got 1 plate here, another plate here, another one here. There's 2 fasteners. So even though we know that this total load is 10 kips, right, so there's 5 here and 5 here, because there's 2 fasteners, the load on each fastener is half that. So let's look at the one fastener in particular. So we're going to have a upper plate, and then we have the middle plate, and then the lower plate. So this is going to be 5 kips, and this is 2.5 kips and 2.5 kips. And that means that the shear here, right, is 2.5 kips, since we have double shear. So our average shear stress is V over A, and so that's going to be equal to 2.5 kips over the area. Well, they told us that it was a 3/4 inch diameter bolt, right? So the area is just 1/4 pi times 0.75 inches squared. And that's going to be equal to 5.66 KSI. So that's the shear stress on those bolts. Done. Let's look at another one. We'll look at let's look at this one up here, 19. Right here. We have an eye bolt. We have a 30 kilonewton load on the eye bolt. It has a diameter of D. And on the back side we have a washer and a nut. Now, one thing I want to point out to you about these fundamental problems, and I encourage you to work more than just the ones that I'm going through right here, is if you look at the back of the book for fundamental problems, and it's the same for the e-text, you'll find that they've worked the problems for you. Now, don't just jump to the back and see how they did it. For example, here's F119 right here. But the right way to do it is to try to work the problem yourself, and then check it with the back of the book to see if you got it right or what you did wrong. So try it yourself first. But still, I thought we'd work a few problems. There's plenty of here for you to do as well. So again, we have this eye bolt. So the question is, we need to look at the question. If the eye bolt is made of a material having a yield stress, sigma y, of 250 MPa, that's a steel by the way, determine the minimum required diameter D of its shank to the nearest millimeter. Now note that they asked to the nearest millimeter. Apply a factor of safety of 1.5 against yielding. when they say nearest millimeter, remember I told you we're conservative, we're going to round up. We're going to want a slightly bigger, even if it's 0.1, we're going to round up. Because to round down would increase your stress above the allowable. I'll show you what I mean. Okay, so here we have the block, and here we have the eye bolt coming out. The hole in the eye bolt. On this side, of course, we've got the washer and the nut. And we said that we had a load on this of 30 kilonewtons. And this has a diameter of D. That's what we're trying to determine. So we know that sigma yield is 250 MPa. And we wanted a factor of safety of 1.5. So that means that our sigma allowable, right, we want to reduce this, is going to be 250 divided by 1.5. And that's equal to 166.7 MPa. And of course we know that the stress itself, right, is just P over A. And we know that the area is going to be equal to 1/4 pi d squared, because we don't know what d is. So we're going to solve for d. Okay, so we're going to put multiply by A over here, divide by sigma over there. So we're going to say that area, right, is equal to P over sigma. And since we know that area is equal to 1/4 pi d squared, we can multiply by 4, and we can divide by pi and take the square root. So it's 4p, right, over pi sigma, and we want the whole thing to the 1/2. And so that's equal to d. All right, so what's that equal to? Let's plug in our numbers. So it's going to be 4 times the load, which is 30 kilonewtons. And that's going to be divided by pi. And we have 166.67 MPa. Okay, so we got to take the square root of that whole thing. And that comes out to a diameter of 15.14 millimeters. Now watch your powers of 10 there, because we had megapascals and kilonewtons, and so you got to be careful with your powers. But you should get 15.14 millimeters. Now, like I said, we're always going to round up, so that means we're going to use a diameter of 16 millimeters. So that's our answer. Okay? So, not very hard. Let's try another one. Let's look at problem number 20. Problem number 20. Now, in the text that I have, your e-text may be corrected. But of course, we're all in English units here, American units, whatever. And they asked for the nearest millimeter. What they really meant was the nearest 1/8 inch. If you look in the answer in the back, it gives you in terms of 1/8 of an inch. So this is just a misprint. So we have this bar here in this figure, and it's made of a material having a yield stress of 50 ksi. So it's again a structural steel. Determine the minimum required dimensions, H1 and H2, to the nearest 1/8 inch, and apply a factor of safety of 1.5 against yielding. Each bar has a thickness of 0.5 inches. So these are flat bars, not round bars. They're not rods. Okay, they're just flat bars. All right, so let's work this little problem. So again, let's write down what we're given. We know that sigma yield is 50 ksi, and we have a factor of safety of 1.5, and the thickness is equal to 0.5 inches. So that means our sigma allowable is just 50 ksi over 1.5. And that's going to be equal to 33.33 ksi. So let's look at our bar. Here's a bar. And this is H2. And this is H1. And we're going to put 30 kips here and 60 here, because on this shoulder we're putting an additional 30 kips, 15 here and 15 here. Okay, so that means in this section we've got 60 kips, and in this section we have 30 kips. So the area 2, right, is going to be equal to 0.5 H2, and the area of 1 is equal to 0.5 H1. Those are in inches squared. And we know that the allowable stress is given. So we take our stress, well, to calculate the area, right, we're going to say stress is equal to P over A, which is equal to P over 0.5 H, whether it's H1 or H2. And then we're just going to, again, multiply by H. So we're going to say that H is equal to 2P over sigma. That's it, right? Because 1/2, put the 2 up top. Yeah, that's right. Okay, so now we can say that H2 is going to be equal to 2 times 60 kips divided by 33.33 ksi, and so H2 has to be equal to 3.6 inches. And we're going to say that H1 is equal to 2 times 30 kips divided by 33.33 ksi, and so H1 is equal to 1.8 inches. Well, you got half the load, so you need half the thickness, right? Half the area. Okay, but that's not the right answer, right? The right answer has to be in terms of eighths of an inch. Well, 6 is pretty close to 5/8, right? 5/8 is 0.625. So we're going to say that H2 is going to be equal to 3 5/8 of an inch. And H1, well, 0.8, if we round up, we're going to get 0.8125, right? 7/8. So that's equal to 1 7/8 inch. So those are the two answers. Okay, next problem. We'll do number 21. Then we'll do one more. So here we've got determine the maximum force P that could be applied to the end of the rod if it's made of a material having a yield stress of 250 MPa. Consider the possibility that failure occurs in the rod and in the section at AA. Apply a factor of safety of 2 against yielding. So here's our rod. Oh, you couldn't see that, could you? Well, I read it to you. There we go. Here's our rod, and here's our cross section at AA. So all we're looking at is this net section through here where this pin goes. Okay. And the load is P. So let's just duplicate that. So we've got a circle here with a hole in it. And then we have a rod coming out here. And that rod has a 40 millimeter diameter. Oh, that's a 0. And P is whatever P is. So that's what we're trying to find. And the cross section with the hole in it is 50 millimeters wide. And this is 120 total, and this is 60 whole. So that means that this is 30 and this is 30. Okay. So if we look at the two areas, the net area here is just going to be 120 minus 60, right, times 50, and that's in millimeters. So we probably want to put that in terms of meters. So that's 0.12. Let's see. So that's millimeters squared. So that's going to be 60 times 50 times 1e6, change sign. So that's going to be 0.003 meters squared. And now the area of the rod is 1/4 pi times 0.04. Now it's in meters squared, which is equal to 0.00126. So we can see just from comparing that to meters. So since this has smaller area, right, the rod fails first. Remember, we're trying to find P. So we know if this is, since this has more area, it's going to have lower stress for the same load. Okay, so let's come back. So we only have to worry about the rod. Well, now that we know the area, we were told that the yield stress is 250 MPa, and the factor of safety is 2. So our allowable stress is just 250 over 2, or 125. Right? The allowable stress is just the yield stress over the factor of safety. 125. Okay. So given that, now we can solve for P. So we know that again, sigma is equal to P over A. So sigma times A is equal to P. So P allowable, right, is going to be equal to sigma allowable, 125 MPa, times the area, which is 0.00126 meters squared. And that comes out to 157.08 times 10 to the third newtons. Now, we really don't want to use that number. So in this case, because again, we want to be conservative, we're going to round down on the load. Right? We're going to round down on the load, not up. Why? Because lower load gives us lower stress. We can't exceed our allowable stress. So we're going to say that the real answer, the P allowable, and plus we want 3 significant digits, is 157 kilonewtons. Okay, there we go. So there's a few fundamental problems. If you want me to work some more, send me an email and I'll make another little video, or we can do them in class. But as you know, we only have limited time in class. So there we go. Best of luck. Talk to you next time.